Hey, Physics 20s. I just wanted to put a little title slide here. Today we're going to go over some dynamics word problems that you guys are going to have the week to work through. There's going to be a lot of independent work, some homework. Of course, Mr. Zuninch and I will be here for office hours, 9 to 11 and 1 till 3 every day. I just wanted to put up this title slide here because we want to make sure that we're focused on the most important parts of Physics 20 that are going to prepare you from Physics 30. So I know some of you guys are sometimes in the habit of like, okay, well, if I'm assigned these questions, I'm going to do all the questions to prepare best for quizzes or exams and stuff like that. And because of all the limitations that we have, we're only going to select certain portions of the course to teach you guys for the remainder of the semester. So this is a sample of dynamics word problems from chapter 3. It is not recommended that you go just try something on your own. Like, you can try it, but it won't be tested. It won't be part of the course. So just focus on the stuff that we're emphasizing, and then we'll be good from there.
Problem number 1. A person and an elevator have a combined mass of 720 kilograms. If the elevator cable exerts an upward force of 6,750 newtons on the elevator, find the acceleration of the elevator. Okay, so here we've got two forces acting on the elevator, one pulling up, one pulling down. What we're going to do is we're going to draw a free body diagram of the elevator. And that shows the forces acting over the elevator as vector arrows coming from a dot in the middle. So it allows us to keep track of multiple forces. So we've got one force up here, and that's the tension, 6,750 newtons. And then we've got weight acting down. And we don't know the magnitude of that force yet because we haven't calculated. We know the mass. I'm going to wait to calculate the weight before I draw the arrow in, because I don't know if it's bigger than the tension or smaller than the tension. So I'm going to find that out. So I'm going to find the weight of the elevator. 720 kilograms times 9.81 meters per second squared. I get the weight to be 7,063.2 newtons. Obviously, that would be acting down. So notice it is bigger. So we're going to make sure, and we're going to draw this vector arrow pointing down longer than the one that is pointing up, because bigger magnitude means bigger force. I mean longer, well, bigger force and also longer arrow. So 7,063.2 newtons. Okay, so we've got one force acting up, the other force acting down. What we're going to do now is use our free body diagram to write an expression for the net force. And the net or unbalanced force is the vector sum of the forces acting on the object. And here we've got two of them. And by vector sum, we mean we have to include direction. So we're going to choose up to be the positive direction. So positive 6,750 newtons plus negative 7,063. And we get the net force to be negative 313 newtons. We just didn't write down the 0.2 there, the decimal place, but we kept it in our calculator. So that means, obviously, again, that negative sign means that the net force is down. So then to determine the acceleration of the elevator, net force divided by the mass, net force negative 313 newtons, which means, again, down, mass 720 kilograms, and to three significant digits, we've got the acceleration to be negative 0.435. So again, that negative sign means down, so our answer then is going to be 0.435 meters per second squared down. Okay, next word problem. A 20 kilogram sign is suspended by 2 ropes. Determine the tension in each rope. Okay, so the sign is just hanging there. So what we talk about is this sign is in what we call dynamic equilibrium. So what that means is all forces are balanced. It's not accelerating left, right, up, down. It's not moving. So therefore, all the forces pulling on it and pushing on it or whatever have to be canceling each other out. So let's see. Well, we know for sure that gravity is going to be pulling down on this sign. So what we're going to do is we're going to calculate the weight of the sign. Because when we do that, here's what our free body diagram is going to look like again. Draw these free body diagrams to keep track of multiple forces. So here we've got the sign, kind of like that. Dot in the middle, we have the weight acting down. We've got one rope pulling to the right. We'll call that FT1, T for tension. And we'll call this one FT2. So it's kind of up like this. So we've got 3 forces acting. We don't know the tension forces. We don't know what that one is, and we don't know what that one is. That's what we're trying to find. But we can, however, find the weight, the force that's pulling down. So for the weight, the mass of the sign is 20 kilograms. Acceleration due to gravity, 9.81 meters per second squared. We get the magnitude of the weight, the force pulling down on the sign, as 196.2 newtons. Oops. 196.2 newtons down. So that's what that is. Okay. Now, here's where we deal with vectors at different angles, right? We've got this rope is pulling this way to the right, or left, I mean, and this one is pulling that way. Here's what we're going to do. What we'll do is we'll draw ourselves a vector diagram for FT2. Okay, so it's going to be like this. So we've got it's pulling not only to the right like this, but it's also pulling up like that. So we're going to draw this. This angle would be 35 degrees. This would be FT2. So we've got an X component pulling it to the right and a Y component pulling it down. Okay, here's the thing. This sign is in equilibrium. So that means the forces pulling up and down on it balance each other out, and the forces pulling left and right on it balance each other out. So that's what we're going to do. We're going to consider the two perpendicular directions. Let's just do the y direction first. Okay, so for the y direction, the net force in the y direction, there's two forces acting in the y direction. There's gravity pulling down and the y component of the tension in rope 2 pulling up, because rope 1 is only pulling to the left. The only thing that's pulling up on it is the y component of the tension in rope 2. We know that the forces acting on this thing are balanced. So that means the net force in the y direction is 0, or the sum of the y components is 0. And what that means then is that the y component of the tension in rope 2 is equal and opposite to the weight. They have to cancel each other out. So that means then that Ft2y, the y component, has to be 196.2 newtons up. So that's what that is. 196.2 newtons up. Okay, well, notice now for our diagram there for Ft2, we've got our angle of 35 degrees and we've got the opposite, and you want to find the hypotenuse. So opposite and hypotenuse is sine. So the sine of 35 degrees, opposite is the y component, Ft2y, divided by Ft2. So we can find out what that tension is. Okay, so we have 196.2 newtons divided by the sine of 35 degrees. And then we get Ft2 to be 342 newtons, and the direction would be 35 degrees to the horizontal. Okay. So now we've dealt with the y direction. Forces in the y direction are balanced. One force pulling down, one force pulling up. We can do the same thing for the x direction. There's one force on this thing pulling to the left, that is Ft1, and there's one force pulling to the right, which is the x component of Ft2. So we're going to use the same logic. So we'll just kind of flip over here. In the x direction, whoops, there's two things pulling. One is to the left, that's Ft1, and the other is Ft2 x component. We know that the forces acting in the horizontal direction are balanced. Same thing with the vertical direction. So that means these two forces have to be equal and opposite. They have to cancel each other out. Okay, so we'll flip back here and we'll notice from our diagram here to calculate the x component, well, let's see, we've got our y component and we've got our angle. So and you can use, you just found out the hypotenuse as well. This is 342, right? So you could use that if you wanted, but it doesn't really matter. So Ft2x, I'm going to write an expression for that. Tangent of 35 degrees is opposite over, whoops, Ft2y is the opposite side, whoops, over adjacent, Ft2x. So using that diagram right there. So then we can figure out what that x component is. Ft2, so the x component of tension 2 is the y component divided by the tangent of 35 degrees. So 196.2 newtons divided by the tangent of 35 degrees. So Ft2x, therefore, is 280 newtons to the right. So that's what that is. Okay, well, we'll go back to our expression then for the x direction. And for the x direction, those two forces acting left and right on the sign have to be equal and opposite. So if Ft2x is pulling to the right at a force of 280 newtons, that means then the other rope that is pulling to the left has to be that same magnitude. So 280 newtons, but to the left. Okay, let's move on to the next one. A 5.0 kilogram box rests on a frictionless table and is attached to a 3.0 kilogram ball as shown. Determine the acceleration of the box. So this is actually a really standard, like introductory physics kind of a classical question. It even has a name. Not that it's super important, but this will help you in like physics bar trivia or something like that. This is called Atwood's trolley. And we've got two masses here. We'll label them. We'll call this one mass 1. That's 5.0 kilograms. And this is mass 2, 3.0 kilograms. So what's going to happen here, obviously, is gravity is going to pull down on this mass. And then that obviously is going to accelerate mass 2 down. It's also going to accelerate the box mass 1 to the right. Both are going to move simultaneously. Notice they're attached by a rope. So one won't be accelerating faster than the other. They move as one. They are a two-body system. Okay, so let's find out what that force is going to be. We can find out what that is. We're going to call this Fg2, the weight of ball 2. Okay. So 3.0 kilograms, 9.81 meters per second squared. You get that to be 29.43 newtons. Okay. So this is the force that pulls mass 2 down, and it is also the same force that pulls mass 1 to the right. Notice it says in the question or in the problem that it is a frictionless table, so there is no other forces acting on this system. So what we can say is that since this Fg2 is the only force that's acting on the system, it is the force that's pulling the ball down and the box to the right, we call this the net force on the system. It acts on both masses. So that force of 29.43 newtons pulls down and to the right, down on ball 2 and to the right on box 1. So here's what we can do to find out the acceleration, and we're going to call this again the acceleration of the system. Again, it acts on both masses. This is a two mass system, mass 1 and mass 2. So acceleration is net force divided by mass. So we have 29.43 newtons, 5.0 kilograms, and 3.0 kilograms, so obviously 8. So then the acceleration of the system is, you get 3.7 meters per second squared. Okay. So we're asked to find out what is the acceleration of the box. So that's the acceleration of mass 1. We'll call that A1. 3.7 meters per second squared to the right. And we could be also asked to find out the acceleration of the ball. Same magnitude, because again, they're connected by a rope or string or whatever. 3.7 meters per second squared down. Next one. Two masses are hung from a frictionless pulley as shown. If mass 1 is equal to 2.5 kilograms and mass 2 is equal to 4.5 kilograms, determine the acceleration of each mass. Okay, so here we've got mass 2 is 4.5 kilograms. And here we've got a mass 1, 2.5 kilograms. So we can imagine what's going to happen here. When you let this thing go, obviously mass 1, the one on the right, is heavier than the mass on the left. So it's going to accelerate down and it's going to pull mass 1, and they're both going to accelerate at the same time. So M2 is going to go down, M1 is going to go up. And the force that is going to cause that is gravity. Okay, so let's find out the two forces involved, right? So here we've got Fg1 is pulling down on mass 1, Fg2, and I'm going to try and draw a straight line. Draw a longer arrow because it's going to be bigger. Let's find out what those two forces are. So we'll calculate them. Just mg, so we've got 2.5 kilograms, 9.81 meters per second squared. So the magnitude of that force is 24.525 newtons. And the magnitude of the gravitational force pulling down on the second mass can be found to be 44.145 newtons. Okay, so sort of to help ourselves wrap our heads around this, what we can do, if we've got more than one force acting on an object, in this case two objects here, best to draw a free body diagram to sort of keep track of things. So here we've got FG1 pulling down on the ball. And on the box here, we've got that bigger force pulling down on that, FG2. Because they're attached by a string, FG1 is going to be pulled up this way. Again, we draw that vector arrow longer by FG2, and FG2 is going to be resisted by that force of FG1. But notice that the net force on both is going to be the same, because basically, if you just sort of round it off, just for round terms here, FG1 is, say, around 25 newtons. FG2 is about 44 newtons. So the difference is 19 newtons, 44 minus 25. Well, here, FG2 is that 44 newtons force pulling up, and here we've got that 25 Newton force pulling down. Again, the difference between those two forces is the same, 19 newtons. So that's going to be the net force acting on the system. So that's what we're going to do. We're going to find out what that net force is by just subtracting these two values. So we'll just take the bigger one minus the smaller one, just to give us the magnitude, a positive answer. 44.145 newtons minus 24.525 newtons. So the net force is 19.62 newtons. So that means that force is going to be the force that acts on both masses. Again, this is the net force on the system, and the system consists of two masses. Both masses experience that same net force. The net force acts up on mass 1, and it acts down on mass 2. Just like in the previous problem where you had one force acting down, or that force acting right here, 29.43 newtons is acting down on the ball, and it was also acting to the right on the box. Here, it's not down and right, it's up and down. Okay, so to find out the net force on the system, we just did that. To find out the acceleration of the system, we divide by that sum of those two masses. So 19.62 newtons. Oops, a little bit neater than that. Mass 1, 2.5 kilograms. Mass 2, 4.5 kilograms. So again, your acceleration of the system is 2.8 meters per second squared. So the question asked us then to determine the acceleration of each mass. All right, well, the acceleration of mass 1, it's the one that's going to be accelerating up. So it's going to be 2.8 meters per second squared up. And the acceleration of mass 2, 2.8 meters per second squared down. Okay, last one. Now this is where we're going to get into, I'm going to mention friction here. We're going to skip over a lot of the stuff that it talks about in the textbook in terms you're going to see things like coefficient of friction and stuff like that. It's basically talks about how slippery a surface is. I'll just mention it. We all know that ice is a slippery surface, and asphalt is not a slippery surface. It's very grippy. So if something is very grippy, it's got a high what we call coefficient of friction. But for our purposes, all we're going to do is we're going to consider a problem where I just give you the force of friction. We're just talking about forces here now. Okay, so a 43.0 kilogram sled is sliding down a hill that makes a 14-degree angle with the horizontal. The component of the weight of the sled that pulls it down the hill is 100 newtons. If the acceleration of the sled is 2.04 meters per second squared, determine the force of friction between the snow and the sled. Okay, so before I attack this problem, I just want to draw a proper free body diagram. A proper free body diagram does not show components of vectors. And you'll see what I mean when I draw the diagram that we're actually going to use to solve the problem. But here we've got our incline, 14-degree angle, 14.0 degrees. And here's our sled. Okay. We know that there's going to be a force, like the reason why a sled goes down a hill is because gravity makes it go down the hill. But weight or gravitational force only acts vertically down. Like that's the direction that things are pulled down. The weight acts down, but the force that pulls the sled down the incline is a component of the weight, which we'll draw in a second. The other forces acting would be, well, the normal forces exerted up from the surface, and then friction would be actually get to slow it down like that. Okay, so that is our properly drawn free body diagram for this situation. But we're not going to, this is not useful for us because essentially here's what we're going to do. We're going to simplify it for ourselves. We're going to call this I'm going to put it in quotes because it's not an official physics thing, a situational diagram. One that attacks the problem that we're trying to solve here. So we'll draw our incline. Here's our 14.0 degree angle. And now we've got this. We've got a sled that's accelerating down a hill. And we've got friction acting in this direction. We're trying to find out what that force of friction is. We are given that the component of the weight that acts parallel to the incline, and just drew two lines that are parallel to each other to represent parallel, is 100 newtons. So now it's like almost a tug of war. You got two forces acting. It's sort of like the elevator. For the elevator, we had tension up, weight down. Here we've got a force pulling it down the hill, 100 newtons, and a force resisting that, pointing up the hill, which would be friction. And you're given a value of the net force. You're given the value of the acceleration. The acceleration of the sled is 2.04 meters per second squared down the hill. Okay, so here we've got two forces acting. We've got Fg parallel, and we've got the force due to friction. So that is an expression for the net force based on our situational diagram. We got two forces acting on the sled, one down the hill, one up the hill, and our expression for the net force is of an expression of the vector sum of those two forces. So we are given the acceleration, and we also know the mass, and we know from Newton's second law, acceleration net force divided by mass, net force mass times acceleration. Mass of the sled is, where is that, 43.0 kilograms. 2.04 meters per second squared. We're going to make down the hill be a negative direction, up the hill being positive. So multiply those two together, you get 87.72 newtons. And again, this negative sign means down the hill. So we are given FG parallel, it's right there. We just calculated net force, and we're trying to find out what's the force due to friction. All right, well, force due to friction, we'll solve that expression for FF. Fnet minus FG parallel, net force is negative 87.72 newtons, indicating down the hill, minus 100 newtons, again, down the hill. So when you subtract those two, subtract them, we get a positive value. We get 12.3 newtons when you round it off. So that's the answer to our question. Positive sign indicating up the hill. 12.3 newtons up the hill.
Okay, that's it for the word problems. You can see that you got a bunch to work on. More ado, you're better off your B again. Concentrate on those very selected ones, and make sure and drop by for office hours again, 9 to 11, 1 till 3. See you guys then.